Okay, so today we are going to learn about curve fitting, or otherwise known as also regression analysis. And curve fitting is kind of similar to interpolation, but there are some uh, but the concept is a bit different here. So let's understand what is curve fitting. And similar to interpolation, here we also have a set of data points. My pencil is not working. It's connected, but yes, okay. Similar to interpolation, here we also have a set of data points, and what we are trying to do here. So in interpolation, what we do, if you have a set of data points, then you want to find a function that passes through all the data points, and if you can obtain that function, then you can also obtain what is the value of the y variable at a random x variable, right? Suppose you have some x and y data points, and after the interpolation, then you can find the y data point at any arbitrary x data point, right? Suppose you have the data points at 1 as 3.1, and at x equal to 2 you have y as 5.9. Suppose you want to find what is the y value at x equal to 1.5, then you have to do interpolation. But here the fitting is a bit different here. What is curve fitting? In curve fitting, you want to find a approximate function that may not pass through all the data points, right? So that function you find here, the fitting curve, that may not pass through all the data points, and that function is just this function here we are fitting is just an approximate function that actually fits the data set, right? So here what is curve fitting? Here I have written that curve fitting of these data points means that we need to find a function that best represents the data by minimizing the difference between the actual data and the predicted values from the function. Here you just need to minimize the difference between the actual data and the predicted values from the function. Here the function should not pass or may not pass through all the data points. It is just a approximate function that minimizes the difference between the actual data and the predicted values of the function, right? So when we do such experiments in school, what we try to do, so in Ohm's law, in 11th class, when we try to verify the Ohm's law in while doing our experiments, so we obtain the I versus V data, right? So voltage versus current data we obtain, and when we try to fit it to find the slope, right? From the slope you can find what is the resistance of that given wire, and when we try to fit the data by hand, what we try to do, we try to find the line that passes through maximum number of lines, maximum number of points, right? We kind of try to do the line that passes through the maximum number of points, right? That we do when we were in school. But is that true? Is that the correct fitted curve for your data points? That may not be true, right? The actual fitted curve may not pass through any single data point. That is also a possibility. So So we need to just minimize the difference between the actual data and the predicted values from this function that we are going to fit, right? And there are many methods to do this curve fitting. We are going to learn about just one method, that is known as the least square method. And in the least square method, there is linear fit, there is polynomial fit, and there are other higher order fitting is present. So we are going to just discuss about the linear fit and the polynomial fit or the non-linear fit of the order 2, quadratic fit kind of, right? So let's discuss about it now. So what is least square method? And in this method, first let's discuss about the linear fit. In this linear fit, we fit the data set with a straight line, right? We just take that the data points are represented by a straight line, and the equation of the straight line can be written like this: y equals to a0 plus a1x, and the given data points may or may not fall on the assumed line, right? In general, the points may be scattered on the either side of the line. That is also a possibility. Then what we do? We found the error function, right? The error function is defined like this. And what this error function means? It means the y predicted minus the y actual value and its square, right? So here the error function is defined like this. This is what? This is this a0, a1 xi, it is just yi, right? And this is the predicted or the function we are approximating, right? So we are approximating that this function is a straight line. The function that represents the data is a straight line, and this is the y predicted value, and this y is the actual value, and the difference between them, take the difference between them and take their square and add them. I is equal to 1 to n, right? All the data points, for all the data points you have, I equals to 1 to n. Suppose you have n number of data points and add them together, then you will find the error function. And the best fit, for the best fit, this error should be minimum with respect to the chosen parameters. So what are the parameters here? This for this straight line, it is a0 and a1, right? And if this is the best fit, if this function is the best fit, then this error should be minimum. This error function means the difference between the predicted values and the actual values, that should be minimum with respect to the chosen parameters. So we need to choose parameters a0 and a1 such that the error will be minimum. And how to find the minimum, the parameters that minimizes this error? By simply taking their partial derivatives, right? So this the partial derivative of this function with respect to a0, and then also find the partial derivative of the function with respect to a1, and from that we can find the values of a0 and a1 that minimizes this function, right? The standard procedure to minimize any function, right? Is it okay, or is there any doubt? Okay. So this way we proceed. The standard procedure to find a minimum of a function or maximum of a function can also be found in this way. So here we are first taking the derivative of this function here with respect to a0, right? So take the partial derivative of this function with respect to a0. and here you see that the summation symbol is now outside, and we are taking the partial derivative of this function here. And if you take the partial derivative, this 2 will be here now, and the partial derivative of this thing here with respect to a0, but it will be just 1, right? So that is why we are getting this. And if you now take the summation, right, take the summation of this whole term here, then this a0 will be added n times. So the term here is n a0, right? And then the a1 will be outside, and take the summation of xi is there, and then take this yi to this side, and the summation of yi is given here, right? Or is there any problem? It is correct, right? Yeah. Now, so then take the derivative of this error function with respect to a1, right? Now take the derivative. So here, let's see. Take the summation symbol outside and take the partial derivative of this function again with respect to a1, not a0. And if you take the derivatives, it will be like this, and there is just this term here xi, and that comes from the partial derivative of this term, and the partial derivatives of other terms will be 0, right? So this xi is there, multiply this xi throughout this equation and take the summations. And here in the first term it will be a0 and summation of xi, and then a1 will be outside from here, and this is the summation of xi square. This is xi multiplied here, xi square, and here for this term it will be summation over xi yi. So we get two equations from this minimization procedure, right? This equation 3 and this equation 2, and they are in terms of a0 and a1, right? And these quantities are just coefficients of parameters a0 and a1. So we can write them in this matrix form, right? For this a0, for this first equation, for this equation 2, this can be represented as this n and xi in the row, and a0 ai into in column, and the right hand side is just summation of yi. And for the second equation, this is represented as in this second row, the coefficient of a0 is this summation of xi, the coefficient of a1 is just xi square summation, and the right hand side is summation over xi yi, right? So then how to find this a0 and a1? You can choose any method, right? Now we are going to do just take the inverse of this matrix and just multiply here, right? Take this to this side, and this will be the inverse of that matrix. And here we can also find what is the values of a0 and a1, right? And how to find the inverse of this matrix? We can do it by hand, right? If there is a matrix like A, B, C, D, suppose this is A, then its inverse is DA minus B minus C and divided by its determinant A, right? Do you remember this formula? Yeah, so that is what we are doing here, right? This is a matrix, and its inverse will be what? Just take the DA like this, and this is D, and here it will be in this position, and A will be in this position, and just take the negative of minus B and minus C term, right? And also divide it by their determinant, and then multiply this whole thing with this column vector, and if you multiply this, you will get this column vector again, right? And this is the term equal to A0, right? So we started with A0 and A1 equals to, so this A0 is equal to this quantity here and A1 is equal to this quantity here, right? You finally found what is the value of A0 and A1 that minimizes the difference between the predicted data and the actual data, right? So that is how you do the curve fitting. So you can compute the slope A1 and the intercept A0 from the above formula to get the expression for the fitting curve y equals to A0 and A1x. You got the function, the straight line that represents the data best, right? And now similarly you can do the non-linear fit, that is not linear, and here instead of just taking a straight line, take a quadratic function like of order 2. So the polynomial of degree 2, right? So this is your predicted function or predicted data. And going through, if you go through similar calculations, here the error function will be like this, and it will have three parameters, a0, a1 and a2, and this is the difference between the predicted data and the actual data, and take their square. And now if you minimize the function with respect to the parameters a0, a1 and a2, you will have a similar matrix as like the previous case, right? In the previous case, you see what was the matrix? The matrix is like n, then here it is xi, and here it is also xi sum, and here is the xi square sum. And see in the next case, here it is also n, and here it is also xi will be there, it is also xi, and instead of writing I am just writing them just like the summation, right? I have emitted the I values, right? So here it will be n, and here it is xi, and here it is also xi, then here it is also x square, and then here this x square will remain through this diagonal, right? Then it will be x3, x to the power 3 and x to the power 3 summation, and finally it will be x to the power 4 summation. It has a kind of a pattern, right? So the pattern will then again emerge here, and you will see, and you will get the values of a0, a1 and a2. And on the right, for this column vector also, you see in the last place it was like y, then x into y, and then in this quadratic case it will be then y, xy, then it will be x square y. And if you solve this for this a0, a1 and a2, then you will get the polynomial fit or quadratic fit or nonlinear fit you can do for the data. Okay, so let's see some programs to implement these methods. We will implement the linear fit method only, and you can also implement this method. See, implementing this method is not a bit difficult, because you just need to find the inverse of this matrix, and the inverse of any matrix you can find anyway. So there are if you are doing it C, then there is a method, and if you are doing in Python, you can also do it in just one line. To inverse a matrix, the method is like this: np dot something like linear algebra inverse of the matrix, right? If this is the matrix A, just input in this function, suppose and assign it to variable A inverse will be just np dot, this np is the numpy, right? Numpy imported as np. So A inverse will be np dot just linear algebra. There is a linear algebra method in the numpy module, right? np dot linear algebra dot inverse A. Just input the matrix here, and you'll get its inverse, and then multiply it with this column vector, and you will get the values of A0, A1 and A2. So now let's see how to implement this in Python. The linear fit. Okay, so let me stop sharing here. And stop. Now can you see my screen? Okay. So here we are going to do the linear fit. Of the data points we have in our first table, right? So let me open the first table. Right, this is the data set we have, right? Suppose this is the voltage and this is the current values, and here is the data set. Here this x is the voltage values and this y is the current values, right? Here I have written them in a numpy array. First we are importing numpy as np, then matplotlib pyplot as plt to plot the data points. So first we are plotting these data points here, right? They are not in a straight line, but we are going to fit these data points with a straight line, and the method is the least square method, and we are going to do the linear fit. Okay, the x data points are actually this. So here what I have written, this x is capital X. Suppose that means the small x or the x data points are actually this array here, and this y is the capital Y, right? Or if it is confusing, then we can also write it is like this. These are the voltage values and these are the current values, right? Let me run it. Yes, then also this. What is the error? Name capital X. Oh, sorry. Then it will be like I will be on x axis and V will be on y axis, and the label will be I. Yeah, V will be on y axis, right? No, here yes. Yes. So here V will be on x axis and I will be on y axis. Then x label is V and y label is I, right? Then run it. It is like this. Yes, as we are increasing the voltage up to 10 volt, and we are getting the current values, right? Okay, now on the x-axis we have the voltage V, and on the y-axis we have the currents, right? So x is V and y is I, and what is n? N is the length of that, length of x, suppose, right? How many data points you have in your array, and what are these now? This sx2, sxy, sx and sy. So this sx2 means this x square summation, right? So do we have the note? Or is the note? Yes. So there are these summations, right? If you see, yes, here there are these summations. So the summation of xi means the sum of all the x data points, and here you also have the sum of the x square data points, right? So you also need to find these summations, right? So that is what we are going to do here. So first we assume that the summations are 0. The initial values are 0, and as we go through the for loop, we will update their values, right? So for I in range n, means for all the data points, the summation will go like this. The sx2 value is xi into xi, right? Xi square, you are adding the square values to this variable, and this sxy is xi into yi, right? And what is this sx value? It is just the summation of xi, and what is this sy value? It is the summation of the y values, right? As you need all these data points, right? All these quantities. Here it is xi summation and xi square summation, this yi summation in this column vector here, and also this xi yi summation here, right? So that is what we are doing here. Okay, let's go back to our, yeah. Then what is a1? What is the value of a1? Okay, so my battery was less. Okay, so what is the value of a0? A0, yes, here. Yeah, that is the value of a0. A0 value is xi square, then multiplied by yi minus this xi into xi yi summation, and divided by this quantity here, right? And that is what we have written here. Here if you can see that this a0 value is this sy into sx square, means summation of x square, summation of y, minus the summation of x and the summation of xy, and divided by the denominator here, right? In this quantity here, right? And that is the value of a0. And similarly we have written the value of a1. First we are doing the summations in this for loop, and then after that we are putting all these summation values in this a0 and a1 quantities, right? Now print a0 and a1. If I run them, it will run, and then if I again run them, it will be printing this a0 and a1 values. And now if you have the a0 and a1 values, you have now the predicted or the approximate linear function or the straight line. and the function is a1x plus a0, right? And now if you plot all these data points and the function together, the function we predicted from the a1 and the a0 values, then you will get the fitted data, right? These are the data points, and this is the actual curve that actually fits the database, right? It may not pass through all the data points very closely, but this function actually represents the best fitted curve, right? Initially we may do like this. If you are in 11th class, you may fit the points like this, right? But that is actually not true, right? That is may not be the best fitted curve, but this is the best fitted curve. And here we are plotting them, right? So that is how you do the linear fit. And similarly you can also do the non-linear curve fitting, and that you can see in that book I have recommended, and that is very easy to do, not very difficult. You just need to know what is the basic. Now is there any doubt or is there a question? Okay then. Okay, so that's it for today. We discussed about the basics of curve fitting, and if you want to explore more, you may go through the books I have recommended, and there are also some tests for it, right? How to test the accuracy of that of this regression or that curve fitting, and there are the test the important test is known as the uh, that chi-square or the CHI squared test, right? I don't know the proper pronunciation, right? And there is the chi state or the chi-square state, right? Do you know about them? Yeah. Okay, so you can read about them from the books, and that is important. I have seen them in the syllabus of in the syllabus of the research aptitude that appears in the PhD entrance exams. In the research aptitude syllabus, there are these things: the regression analysis, the curve fitting, the chi-square state test, and means how to test that that this curve fitting is accurate. What is the accuracy of that curve fitting? So there are tests to do it. Means you need to find just a quantity to test how much accurate is this curve fitting. If you are doing any kind of research to fit the data points, you need these methods, and then you need to provide the accuracy of your curve fitting, and that is where this chi-square test comes in. Okay, so that is all about today. Okay, so let's meet tomorrow, and tomorrow we will discuss about the roots of algebraic equations and transcendental equations. Okay, so yeah, so that is it for today. So bye then. Bye.